Hello, everyone. My name is Sebastian Keller. I'm a systems engineer at Arista, and I will be your host today for this webinar titled The Next Generation of Live IP Production. Joining me today, we have Gerard Phillips from Arista, who is a technical solutions architect, and Henry Alexander, CEO of SDNsquare. Over this 1-hour webinar, we will go through various topics such as the architecture of physical network for live IP production. We will go over SDNsquare approach to SDN. We will try to explain to you why live production networks are different from normal networks. And we will also see 3 different case studies. During the course of the webinar, we will be answering questions. However, for this, please use the Q&A button and not the chat, and do not use the chat window. We will not be able to answer this question asked through the chat windows. With that said, it is my pleasure to hand it over to Gerard Phillips.
Hey Seb, thank you very much for that introduction. So I'm going to just provide a very brief overview of Arista Networks to start off with. We've been transforming networking for quite a while now. Our first switches hit the market in 2008, where we provided low latency, great multicast and great PTP functionality in our switching platforms, which were targeted at the high frequency trading guys. So those are the guys that really needed the multicast scale and the PTP reliability. We followed that up quickly with a bunch of switches that targeted the cloud titans, where standard support, visibility, programmability, and reliability at scale are massively important. And quite recently, in the last 4 or 5 years, 5 years maybe, we worked out that those 2 sets of customers really had all their requirements were matched by what the media entertainment live production guys needed. The multicast scale and accuracy, the PTP reliability, the ability to have programmability and visibility in the network. It's exactly what our broadcast customers need for live production. And so we've been targeting that market for some time now. So what we're going to talk about today is how we can bring a difference to live production for 2110, 2022, AES67, those live production technologies. So I'll hand over now to Henry, who will give you a quick introduction to SDNsquare.
Hello, everyone. SDNsquare is a young company based in Belgium. So we're based in Ghent in Belgium, and we're composed of a unique team of experts with really hands-on experience on advanced broadcast and IT technology. We develop and we market software products that are solving cost, performance, and scalability issues in the growing large-scale media processing, storage, and network platform. We do that in a unique way as we package the complexity, the design, and the operational engineering effort into a very intuitive software to be as simple as an engineer in a box. So we're moving to an IP world, and moving to an IP-based live production model is challenging. It's challenging in terms of reliability, in terms of training, in terms of operation. We want at SDNsquare to solve these issues by automating and controlling the platform. We're facing the challenges of the IP network with a very simple approach, but very also advanced approach of software-defined network controller. So that's why I will give the word now to Jara Phillips from Arista to explain the architectural choice for a software-defined network controller.
Thank you. So yeah, I'll spend a little bit of time talking about why SDN is required, and I'll talk a little bit about some network architectural choices that you could that are open to you guys as broadcasters, and a lot of these will be network. There'll be architectures we've already delivered to customers who are on air now, and so these are tried and tested architectures that are really well suited to the high reliability, high performance world of live IP production. So I'm going to give a very quick recap on multicast. We use multicast in this world because we're looking at a one-to-many or in some cases many-to-many model, typically a one-to-many. Unicast doesn't do that. Multicast does that. Multicast allows you to deliver traffic to more than one receiver. So in this world, senders send, we have a camera down the bottom there. Receivers request data via IGMP requests. In this case, you can see two, a multi-viewer and a vision mixer are trying to pull the flow from that camera. And in an IGMP world, the network determines the path. So open standards, IGMP, PIM are used in the network to deliver traffic from the camera to the two devices in this drawing that are looking to have that delivered to them. So replication happens in the fabric of the network, which means that we're not wasting bandwidth sending the image twice from the camera. It's very simple because it's standards based. You know, all the vendors, most of the vendors support this. And it's simple in the sense that there's no external controller required. So you see in the top right, we have a broadcast controller, we have a device controller. There's no need for anything other than a sender to send and a receiver to ask. And once the network is configured, those flows will be delivered. I've thrown in the bottom layer 3, flexible and scalable. The audio guys, AES67, Dante, Ravenna guys, have been doing this stuff for a long time using IGMP, typically over layer 2 networks or often over layer 2 networks. I'm going to just be very clear that our recommendations are layer 3 networks in order to get the scalability that you guys are after at the bandwidths that this media is flowing at. So if IGMP is that good, you know, what's not to love about that, right? And it's definitely the case that for many applications, IGMP is absolutely the right way to go. Simple, interoperable, works, no problems with it at all. But there's just some stuff that you need to be aware of. So IGMP and PIM, they are not link capacity aware. They don't know that you have a 10 gig link or a 100 gig link or a 400 gig link. And so the requests will come and the network will attempt to fulfill those requests. If the system ends up pulling too much traffic, well, that just causes congestion, that causes traffic loss. That's no good in our environment. Also not source bandwidth aware. So is that camera generating a 1 gig flow or a 3 gig flow or a 10 gig flow or a 400 megabit flow? IGMP and PIM just don't know. They don't care. They're just going to try and deliver that for you. So a system that's working today may stop working tomorrow if you convert the camera from 3 gig to 10 gig, if you flip from 1080p to UHD. And there is no, IGMP and PIM don't provide dynamic load balancing. They provide, typically they provide a hash-based balancing for LACP or ECMP. So in the case, we've got two points in case here. So if from the camera there are multiple uplinks to the spines, I've just shown one, but imagine they've all got multiple uplinks. The balancing that happens across those multiple uplinks is not bandwidth aware in an IGMP PIM system. It's a statistical hashing. If all of the flows came from the same source IP, going to the same destination IP with the same UDP port, there's a fair chance they'll all end up on the same link. So that again is not scalable. You end up having to design your networks to be have overcapacity to cope with that. And the second case where it's not dynamically load balanced is where you have multiple spines. You can see here that camera could bounce through multiple spines to get to the endpoints, or could go through either of the spines. Either of the spines are connected. IGMP and PIM don't know which one it's going through. There's no load balancing that makes sure that one set of uplinks is loaded similarly to the other set of uplinks. And I called it application aware. I couldn't really think of a better word. What I mean is if you take a spine out for maintenance, upgrade the software, I don't know, something else, whatever else you might need to do. BGP, you can drain the routes from BGP. So from an underlay unicast point of view, that can be relatively painless. But the IGMP and PIM system don't know that that bandwidth has gone away. In fact, there's now the same bandwidth and fewer spines. So that tells you that you're now going to have less traffic possibly, or have had less traffic to begin with. So IGMP and PIM, great in relatively simple systems. So if it's not great for all systems, what do we need? What we need is, and forgive my very basic analogy here, we need something that is more aware than a paper map. A paper map will tell us how to get from leaf A to leaf B, but it doesn't tell us about roadworks, it doesn't tell us about traffic jams, it doesn't tell us about diversions, it doesn't tell us how big the road is, doesn't tell us lots and lots of stuff. It doesn't tell us that at 3:30 every day, there's a load of people going to school with their kids, coming home from school with their kids. So the alternative to IGMP is some sort of software-defined networking where we separate the control plane and the data plane. And we have an external orchestrator, in this case, I've called it a network controller, that makes or influences the forwarding decisions in the network. So those forwarding decisions are not based now on multicast group addresses. They're not based on IGMP and PIM. They're externally determined. So I need to get from the camera to the multi-viewer. The external system works out the best way to get there based on the current traffic and based on the traffic that the camera will generate. And that means that you can then start to take diversions around roads that are shut. It means you can start to understand that if a motorway is down to 1 lane rather than 2 lanes, then you've got to have less traffic. We're basically pushing the intelligence into this external network controller. And in practice, what does that look like? So in practice, what that looks like is, you can see on the right-hand side, there's a typical stack. You've got a broadcast controller at the top. That's got a bunch of device controllers. No change there, right? But we've added in this network controller. And the network controller, the job of that is to understand the traffic in the network, understand the sources in the network, and understand the topology of the network, and to make choices and direct how the traffic will get from the camera to the multi-viewer and the camera to the vision mixer, for example, in this case. So separating out the responsibilities. The broadcast controller remains the same as you've already got. It's the same bit of software you've already got running your system today. It understands XY panels. It understands being automated. It understands how to connect logical signals together. The network control, it still tells the device controller to tell endpoints to do things, but it now tells the network controller to provision a path. So the broadcast controller still does all the stuff it used to do: tie lines, levels, matrices, audio, follow video, still has scheduling. It still does all the things that you currently have. What you've added in is this system-wide view in the network controller, which is topology and bandwidth aware, and which you can then use to start doing smart stuff like taking paths down in the case of failures, rerouting in the case of maintenance, that sort of stuff. So I hope that's a reasonable, simple introduction to SDN. I want to talk a little bit about some of the architectures that we see out there now, and how and when SDN becomes useful in those architectures. So probably, I'd say 60, 70, 80%, 70%, let's call it 70% of the systems out there that are 2022/2110 today are fairly simple. Typically a couple of big switches or a couple of small switches, depending on the scale. The switches, choose the right switches, their line rate, forwarding, non-blocking, multicast non-blocking. And in those sorts of environments, then, you know, back to the previous slides, IGMP is absolutely fine. The switches are non-blocking. There is nothing to manage in terms of bandwidth. And these early systems, they are very large, really. They're capable of scaling very well. So if you imagine 32 times 100 gig switch is the equivalent of a 576, is the equivalent of a very large SDI router. I don't have the number with me. I deleted that from the slide. That's a silly thing to do. But it's a very, very big SDI router equivalent. That's 32 times 100 gigs, 3.2 terabits a second in both directions. That's a lot of 3 gigabits a second. And if you kind of, you know, as technology moves forwards, then they multiply that by 4 quite happily for 400 gig type capabilities in these switches. You're talking about a very, very big system. Now, the downside, upside is simplicity. Downside is large failure domains, large maintenance domains. If you need to upgrade a switch, you've taken out the whole of your red network or the whole of your blue network. And that may be okay, and it certainly is working very well for a lot of people out there. Also, you've got fewer connectivity options. You've got these 2 big switches in the probably in your central apparatus room, and they you've got to get to all your endpoints from those 2 switches. So you're giving yourself potentially a bit of a cabling challenge. But as I say, 60 or 70% of the systems out there look like this. They work very well, very simple. What I'm seeing is a lot of people who are, I'd say 60 or 70% of the people I talk to now are looking to move to a more distributed system, a leaf and spine system. So this is the data center model. This is what Google, Microsoft, all those guys look like. Simple, scalable, repeatable, resilient, very, very simple template. If you want more capacity, put bigger spines in, put more spines in, add more leaves. It's a very, very scalable architecture. The nice thing for us is everywhere is only ever 3 hops away maximum, leaf, spine, leaf. So the latencies are very low and deterministic. Obviously they're lower if you're on the same leaf, but fundamentally you're not really very far away from anywhere. And because you've got the leaf structure, it's easy to keep adding stuff, and it's easy to accommodate a wide range of end device interface speeds. For example, you can have a 1 gig audio leaf, you can have a 10 gig video leaf, you can have a 25 or 100 gig video leaf. So quite a lot more flexible. Smaller physical failure domains. If you lose a leaf or you put a spine into maintenance, it's a much smaller proportion of your network. But these guys, these networks tend not to be built as non-blocking, because that would be quite expensive. They tend to be built with an understanding that they are blocking networks, at which point we absolutely do need some sort of orchestration to manage that bandwidth resource. It's a resource management thing. So some sort of network controller driven by the broadcast controller protects the 2110 AES67 2022 delicate flows, and potentially can add workflow security and can contribute to multiple tenancy if that's what you need. A lot of people talk about red and blue air gap networks. So the -7 capacity of 2022, 2110 and AES67 means that we can be resilient to lost packets and to damaged networks or maintained networks. Most of the networks we've seen so far, in fact, all the networks I've seen really have been red and blue. So you have a red network and a blue network. In that case, in this case, we've got a leaf and spine, so SDN controller would be recommended. But very simple architecture, no possibility of any failure in the diverse paths of the red and the blue. You can see the camera goes to the red network and it goes to the blue network, and it's delivered to the multi-viewer through the red network and the blue network. Very, very secure. But for example, the microphone, is a single-ended device, and it's only available in the red network. We can't get to that anywhere else. So that may be something that is a disadvantage for some people. Hybrid networks, we're seeing these starting to pop up. So we have these purple switches, which are places which are connected to both networks. We limit the number of those and we limit what we plug into them, but it gives us somewhere where we can add these single-ended devices. Now, a single-ended source is a very easy thing to consider. The flow goes in, gets replicated and sent to both networks. Single-ended receivers are a little bit more tricky and need some more kind of orchestration in the broadcast controller stroke device manager, but entirely doable as well. Still, from an SDN point of view, still relatively straightforward because most of the path diversity is provided by the red-blue networks, but a bit more flexible. And what we're starting to see a lot of conversations about now is all purple networks. Now, an all purple network is much more like the data center architecture in the sense that data centers don't have red and blue networks, they just have a network. So here we see it's the same number of switches, it's got the same capacity. I've missed out the purple switch, don't worry about that. It's got the same number of switches, the same basic capacity, but it's all shared now. So it's now a series of, it's a red and a blue virtual network sat on top of a purple physical network. So at this point, SDN becomes absolutely mandatory because what we have to do is we have to create logical red and blue paths through a purple network. Now that's something that is completely not possible without the SDN network controller sat there doing that job for you. So the upside is a much more flexible network. You can, if you have any network outages, they can be, you can manage that to be or maintenance, you can manage that to be a limited number of -7 flows or the same amount of resilience, but across a fewer number of flows, or less resilience, but the same number of flows you had before. But those are choices that wouldn't have been available before in a red-blue network. So quite a lot more flexible, but with the requirement that the SDN controller can understand and manage the logical diversity through this physical network. So kind of to wrap this little section up, the leaf and spine architecture, very flexible. In reality, you as a customer still have all the options. You can build a monolithic or a hub and spoke or a leaf and spine. As you make the network topology more complex, you are pushing down the path of having to have some sort of network controller to manage that for you, but you are giving yourself a lot more flexibility, potentially more ways that you can manage the network in the case of maintenance or in the case of failures. That was my architectural section. Seb, do we have any questions in yet?
So yes, I think we have a question for you, Jared. And the question is, if I plan to start small to build my experience, how can I do that simply? And do I need to add SDN at this point? Okay,
great question. Let me go back to this set of slides. Yeah, I hear this a lot. So somebody's looking to start doing a bit of 2110 as a small chunk of their network, or to maybe as a bit of monitoring network. Absolutely, you can start as small as you like. You can think about building a network which is either just a pair of leaves, and as I said before, a leaf pair is still pretty big in 2110 terms. So you could start with a leaf pair, and you could add more leaves and obviously add spines to connect that together later on. Or some people start with a pair of devices that they can later promote to be the spines and add more leaves. In the case of starting small with a couple of leaves, then sure, you don't need SDN at that point. I would say it's well worth thinking about SDN, and it's well worth thinking about potentially implementing the SDN at that point, because you obviously have intentions to grow and you have intentions to learn about SDN. And I don't meet many customers who tell me that they've got big maintenance windows. So if you're looking to build a system and grow it, I would definitely be thinking about adding the SDN early in order to A, gain experience, and B, have a smaller transition as you grow the network, smaller downtime as you grow the network. Great. If there's nothing else, I'll pass on to Henry.
Thank you, Jared. Thank you for all these explanations. Very clear. Many challenges, of course, that we can see. And well, the good news is that SDNsquare is offering a solution to those challenges, and the solution is called Grid. Grid is our unique software-defined network controller software platform, which will allow to design and configure a non-blocking IP network for any kind of converged media flow, and also with very guaranteed and predictable and reliable quality of service. This is a key element, of course, is to guarantee this quality of service at 100%. So we will work in a way where it will be cost effective and scalable. And as you mentioned, Jared, the flexibility and scalability are also key elements in implementing software-defined network controller. So where does software-defined network controller fit, actually, is the layer, software layer between the broadcast management system and the networking hardware and the IP and SDI gateways, all kind of end devices. So we're really sitting in the middle. We're the software layer that really allow to control the full network. More accurately, what is needed for the SDN controller to be implemented. So the use case of the customer could be anything, could be an OB track production, it could be a live IP event, it could be non-live, it could be studio data center. So SDN Grid will fit in the middle of these installations, and talking on the node-bound side with automation broadcast controller software such as Axon, Lavo, Human Interface, and or other monitoring tools such as Skyline. So for that, we will interface with APIs and using NMOS IS 06. So many interfaces are possible here, whether they are also proprietary from the vendor. We're very open to interface with them. On the lower side, on the network side, we interface with the Arista switches very deeply. We are supporting many of these switches, but we're focusing much more on the top of rack switches, as we're proposing a very unique approach of the network control. So what is the, sorry, a little bit too fast here. So what is the unique approach between SDNsquare technology and Arista? Well, we can find it in three aspects. The first one is to be able to determine the routing for non-blocking multicast and unicast. So we can guarantee any type of flows, whether it's specific on demand, with low latency for each path of your network. So scalability, flexible architecture, and the use of 100% of the bandwidth is a key element for us. We do not recommend to over provision, as we have a full control of the bandwidth, and we can guarantee the utilization of 100% of the link. Therefore, we can also provide a full redundancy for any flow, whether it is in a purple network or a full red and blue network. It doesn't really matter to us. The redundancy is a key key element of network architecture. But also guaranteeing the quality of service per flow or per flow class means managing the buffers of the switch. And this is what makes us unique. By managing the buffer of the switches and of the chipset of the switches, we can process the internal packets and schedule the internal packets in a way that any kind of workflows, any kind of flows are fully guaranteed and could be switched very, very efficiently and very fast. So we can therefore also make that network fully converged and redundant by adding many important aspects like discovering devices, configurations of devices, automatic generations of command lines. This is very important, and then that will really accelerate the implementation and the configuration of a network. Also, we can, for any kind of traffic, video, audio, KVM, live IP, file-based, file transfer, software devices, virtualized applications, microservices, we can put them all in the same single network. Last but not least, we do provide a central pool manager with integrated DHCP services and end device module management, and also managing all IP and MAC addresses for all the devices. So these three elements, the deterministic quality of service per flow and converged networking, makes the SDNsquare grid solution and Arista switches unique in the market value proposition. But on top of that, SDNsquare is also providing a very intuitive user interface, which is more than just a user interface to control your network. It's really to design your network. We believe, and that's where we call SDNsquare, we believe that you need to manage your network by starting to designing it properly at the beginning, and to really cancel all kind of error. So you will be able, with a simple, intuitive user interface, to fully simulate an IP network. And this is a key element, as you can work offline and you can really configure everything offline before deploying your network. So now it's time also to give you some word about the real case studies we've been working on. And the first one is one installation that we've started and initiated a little bit more than a year ago in Holland with our partners, United Facilities, part of Euromedy Group. And last April, so 19, they launched the first Dutch program to be remotely produced in full 702110 infrastructure for 24/7 programs, with the majority of the equipment being located in the so-called Remote Operations Center, ROC, at Hilversum, and the cameras in the studio being based and installed in Amsterdam studio. For this installation, we have developed a fully redundant red and blue purple network. As Gerard explained previously, the topology we use is fully agnostic. So we can design any type of topology and any type of flexible and scalable spine leaf topology. So we are not monolithic at all, although if you want to, we could be. So the essence of our installation is to make all the network and all the flows 100% predictable with 100% of quality of service. These are the two key elements of any installations we do with SDNsquare Grid and Arista switches. So as I explained, all the traffic runs on one single network, whether it's video, audio, intercom, management, KVM, office and internet, it all runs on the same single network. And this provides, of course, lots of advantages, and not only on the cost side, but also on the management side. As you can see, the scale of these installation is not that big, it's medium for standards. So we're talking about close to 40 switches, more than 350 clients, and close to 600 cables, giving multiple hundreds of guaranteed flows on the single converged network. So the main competence, of course, of such installations are the top-of-rack switches of Arista, alongside with some desktop switches, silent switches for management of Netgear, and combining interfacing with Imagine and Embryonics SDN and IP gateways and processing, LAO equipment for multi-viewers, audio core, and other stage boxes, Sony cameras and vision mixers, Grass Valley vision mixers, Real for the intercom, and the integration with the broadcast controller of Accent Cerebrum and control panels, and the master clock of Tektronix. So all these experience have allowed us to really integrate with many of these devices and to make it work perfectly together. So why live production networks are so different? I think Gerard will explain you that right now.
Yeah, thank you, Henry. I was going to say, Seb, do you have any questions come in so far for Henry?
Yes, I think we have a couple of questions. This one is for Henry. Yes. What are the main issues you've encountered with installing medium, large scale live IP networks? Could you take us through this?
Indeed. Yes, this is a very good question indeed. So the first thing, and of course, I mean, you cannot maybe predict it in the beginning, but the first one were the cabling issues. So implemented cable check within the grid SDN was a key element. So we've implemented these cable check to compare the state which is configured in grid with the actual state of the network based on information where we will detect via LLDP and other paths the faulty cabling. So this is one of the first issue we've encountered and we solved. And I might say that it might seem obvious, but it's not when you start cabling such installation. The other one, which is probably more normal, I would say, it's the IP address configurations, whether it's unicast or multicast, and also the consistency between these addresses. So within grid, we will keep database and IP addresses. So we will keep all the addresses in the databases, and so we will be able also to link multiple sites and tracks environment together. So grid aims to automatically push network config to client who support it and who have and which has an API. Not all clients, unfortunately, nowadays have an API. So then you will need to do it manually. But Grid will keep all this information in the database. We'll also in the Grid keep VLANs and quality of service settings and all the related network settings that are consistent through the network and on all the switches. So these are really the two challenges. So IP address configurations issues and cabling issues. So so to give an example also, which was a really great help with Arista switches, it was on the location-based DHCP. So where devices get an IP address based on the port of the switches to which they are connected. This is a unique feature that we offer at SDNsquare with the Arista switches. So it's very handy when devices get swapped between each other, often like SFP modules could be. So no need to keep a MAC address registry. But of course, this is an optional feature, and normal DHCP is also possible. So these are the main issues actually we've encountered in our simulations.
Thank you. Very interesting. It's maybe not the first one that come to mind, but definitely some where you can save or lose a lot of time depending on how you do it. So we also have a second question, and it is how can you really predict and guarantee the use and the quality of the network?
Yes, this is very key, a key element for grid and for SDN. So we need absolute control over the network. And as I explained before, to do this, we need to take the path, the control of the path in the network in a deterministic approach, and to really control the buffers, the queues, and the schedulers in a way that grid will have an helicopter view of the entire network to enable to see all the links in the network and the available bandwidth on those links. And we will be able, by talking to the Arista switches, talking to the chipset present in the Arista switches, to guarantee these network and to predict all the paths that will be used. So we'll have a full control of every possible path, and we can separate the different flows or the flow classes into different queues. So we'll be able really to utilize the complete bandwidth capacity of the network without compromising the 100% use of that bandwidth for each individual link or path in the network. So this is related, as I explained, to the tight control over the buffer and the queues of the Arista switches that we do at SDN. So it's very granular. The reservation of the bandwidth and the control of the scheduling of every individual traffic streams, and we shape also the flows to eliminate any kind of packet loss. So this is really a key element. So that's how we can predict and guarantee the use of and the quality of the network. Of course, we support that for any kind of topology, whether it's red, blue, and purple. It doesn't really matter. So.
Thank you, Henry. So we'll take some more questions later on, time permitting. But now it is time to hand it over back to Gerard for the next part.
Thank you. So I'll spend a little bit of time explaining why live production networks are different. Although, interestingly, I think, Henry, you just did a brilliant job of explaining why live production networks are different. You're looking to really leverage as much bandwidth through the system as you can. You're looking to really benefit from the tight integration between the network controller and the switch fabric. I'm just going to kind of highlight a few more. We all know what an enterprise network looks like. It's a lot of users attached to a lot of switches watching cat videos. That's kind of not really what we're trying to do for the 2110 AES67 2022 type world. We are talking about high quality video, uncompressed typically, high value video, otherwise it would not be in that uncompressed, wouldn't be using the uncompressed workflow. So really at the top of your mind should be making sure that you've got an infrastructure which is going to provide the right level of performance in terms of quality and reliability primarily, cope with these enormous flow sizes up to 10 or 11 gigabits a second. Enormous multicast scale. If you consider TPC in Switzerland, they're looking at something like 24,000 flows. That's you're starting to look at big multicast tables there, whether they're SDN or whether they're IGMP'd. That's big tables. And of course, for 2110 and AES67, we're looking for scale and performance for our PTP 2059 PTP infrastructure. Those things are not what you generally get out of switches that are not built with the right levels of thought, architecture, reliability, and underlying silicon. There's a couple of things that kind of jump out straight away. Everything is software defined. So having a network operating system that is resilient and well architected is going to help you with reliability and performance. We have an unmolested Linux-based network operating system. Gives us great fault isolation. We can have agents that if an agent has a problem, it'll restart, and it'll restart typically without any issue to the forwarding plane. And that architecture gets you, you can see a little drawing in the middle there. It's a state-based architecture, publish and subscribe, lots of isolation between the different agents. And that gives us reliability and resilience. And it also gives us the ability to really easily cope with any security issues that might happen. You know, if there's a bug in SSH or something else that's pulled in from the Linux community, that's easy enough to patch, and we can do that without causing any trouble to the network. Of course, we use a version of Linux that's, you know, not cutting edge, so it doesn't tend to have those problems. The other big difference is this merchant silicon approach. It allows us to choose the right silicon for the right switch. So whether you need a big buffers, small buffers, whether you need big table sizes, small table sizes, whether you want to optimize for functionality or for price. We can just, you know, we don't have to amortize any ASIC development because somebody else is doing that for us. So we just fit the right ASIC. And interestingly, our single OS sits on top of all of those ASICs. So very easy for us to achieve this stuff timely in a software sense. And the merchant silicon story is great in the sense that we are riding on the back of Moore's law, but actually slightly quicker than Moore's law, because of course the vendors of silicon have historically been catching up with where the x86 guys silicon sizes are. So actually going quicker than Moore's law in terms of doubling density every 12 to 18 months. So double the density, double the speed equals 4 times the performance. You don't get that without merchant silicon. With a complex stack, we need more visibility. Network monitoring, everyone's got some network monitoring, but I think if you look at the difference we have with the 2110 world, it's that we used to have maybe 3 OSI layers: physical layer, coding layer, and then the application. Now we've got the full OSI stack, and so there's a ton of stuff on the right hand side of this slide, which is just IT stuff. It's stuff you need to monitor: PTP, IGMP, PIM, BGP, CRC errors, physical links, security. None of this is about baseband video. What I'm trying to say is there's a lot more stuff in the middle between underneath the applications that you guys are building, and somehow you need to be able to monitor that better. And one of the things that helps you monitor that is using standard Linux. You get a bunch of tools in there: TCP dump, mirroring TCP dump to the CPU. What a great tool that is, amazing. But also our streaming telemetry allows us to stream this data to either third-party tools that can analyze it, or to you know, if you don't want to buy a third-party tool, or write your own to an Arista monitoring tool that will give you very fine-grained, up-to-date, timely information about the status of your network. The 2 pictures on the right-hand side here, one is the Arista Cloud Vision, which is our very IP-centric monitoring configuration tool. But below it is a quick screenshot from Grid. And what I'm trying to highlight here is that I think that in most cases, you're going to need 2 sets of tools: a very IP set, but also one that's abstracted the IP away into the video world, which is the bottom grid view, which shows kind of using APIs to reach into the network to understand what's going on, understand the topology and the connectivity, and present that data which is available in a way that is much more accessible to the broadcast engineer, for example. Back to you, Henry. Give us some more case studies.
Yes, absolutely. Thank you, Jared. So We'll in the next few minutes we'll explain so existing installations but non-live installations, as these projects have been hold on for due to the current crisis we're all facing. So the first one I want to talk about is the one in the UK with CTV OB truck. That truck is pretty much finished, and it was supposed to get started for live Golf Tour production end of April, but as you all know, it couldn't start. So so the equipment is pretty much fully installed, and the software and the network is fully working with full SMT 2110 video streams and PTP v2. So for this project, we have integrated also with Axon Cerebrum with to guarantee the deployment of all the client flows on the network via our node grid API using NMOS IS06. So the redundancy is also fully guaranteed by the use of a full random flexible spine leaf topology, red and blue purple network. Redundancy is really important for us in these installations, in any installation, and this is fully transparent for the user, as we can guarantee a cluster of grid SDN all running with automatic failover in case it's needed. And once again, we aim for 100% predictability in the network with 100% guarantees of bandwidth and quality of service of all flows. So same principle, one single converged network for all the traffic, video, audio, intercom, management, KVM, office, and internet. The size and the scale of these installations is little larger than the one we've done in Holland, with close to 50 switches, 700 clients, and almost 1,000 cables, generating multiple thousands of guaranteed data flows through the network. So the different components are, of course, the Arista switches, top-of-rack switches, and optics, also very important for the quality and reliability of the whole system. Some desktop silent switches of Netgear, and a bunch of other equipment coming from Imagine, Embryonics, Grass Valley, Evertz, Sony, Telex, and many, many Dante devices, which we are allowed to manage as well with the PTP v2. I'd like also to speak about our latest installation, where it's non-live, and you will all understand that it's a very big sport event that couldn't take place this year, and hopefully will take place next year, which we have fully validated in the last few weeks to make sure it will be easily deployed next year. So it's once again a fully redundant red and blue purple network with full SMT 2110 video streams for different production formats, UHD, HDR, HD, and it's fully modular. So the concept of this installation is that it's fully modular, that you can set it up as a very large system, as I said here, with 2 data centers, but you can split it up in several data centers later on after the event takes place. The integration with the broadcast controller or Axon Cerebrum is also a key element in the success of such a large installations, and to get 100% predictability and 100% of use and quality of service of the network. So you see here a few pictures of that validation environment, because it's not live, but the network is fully converged, as I've already explained previously. It's fully distributed, and evolving to a mesh network, spine leaf, subleaf, leaf on leaf. So the converged network so makes it possible through grid to really manage all the in-band NMOS, PTP, RS-232, KVM, file transfers, video and audio, whether it's Dante or SMT2110 or AS67. So the integration on the north and southbound control is a key element for such large setup, and you need to really integrate with familiar intuitive interface for the operators. This is a key element. So you don't need to reinvent the wheel and develop new tools. It's also about talking to each other, interfacing softwares with each other at a very advanced level, and also promoting and operating on a very automated way, because deployment is the key. Easy and fast deployment are the key aspects of such large operations. So this has been possible through different partnerships and R&D talks between Arista, SDNsquare, Imagine, Netgear, Axon, Embryonics, Riddle, Lawo, Sony, and Grass Valley. To give an idea really of the scale of such network, we talk about 8 galleries, 2 data centers, and about 90 modules hosting several Sony and Grass Valley UHD vision mixers, up to 6, close to 40 EVS machines, 8 Lawo cores, 96 IP and legacy UHD cameras, 256 UHD legacy I/O and processing channels, more than 120 UHD IP processing channels and IP channels, and 2 distributed multiviewers with up to 330 head outputs. So the scale is really huge. Hundreds of 3G and UHD sources, thousands of destinations, whether it's 3G or UHD, hundreds of intercoms and 4 wires entries, more than 250 switches, which the noble ones have top of racks Arista switches and the desktop managements of Netgears. So we're talking about 65,000 multicast addresses to be managed, around 2,000 clients and 3,500 cables to be installed. So giving multiple tens of thousands of guaranteed data flows. So this is the largest network we've built so far, and we're really keen to make it live next year when the circumstances will allow. So as we already explained in the previous projects, the main components are obviously the Arista switches with different type of switches, spine and leaves. So 7260 series, 7060 series of Aristas, 7250s, and the new PoE 7020 series of Aristas. So Netgears, Imagine, Embryonics, Lawo, Sony, Grass Valley, Riddle, Axon, they've all been part of these installations, all part of these installations. So what are the challenges? And I explained before with one of the very interesting questions we received a few minutes ago. Yes, very big network. So we had to also to scale up our skills here, because all these switches, all these end devices is the first time we had to face with such a big network. And the cabling issue was also something we had to answer. There were many faulty cable at the beginning with optics and different modules that we had to discover, and we had to make it in a way that it will not slow down the complete installation. The management of IP addresses, as explained before, was also a key element and a key challenge for such an installation. And also, of course, predictability and reliability of such system is a key element. So we could see issues to get consistent configurations for on every switches, whether it's on the VLANs, for the quality of service settings, the routing, the BTP. So how did we answer to these challenges? So Grid provides really automated and consistent deployment for configuring the switches, including VLANs, quality of service, and routing. As explained before, the pool manager is a key element to keep a very accurate inventory of all client IP addresses, which can be configured manually or automatically via DHCP. So this is a key element also. Pushing IP configuration to selected clients that allow it enables faster and error-free deployment is also very important. Keeping the status of every switch and providing an overview of all the existing cabling and other network issue are key elements for deploying such big and large network. And keeping 100% reliable and predictable network with 100% of use of the network is also an element which is absolutely needed in our scenario of using Grid with switches. So at the end of the day also, it all relies also on the expertise of the people and supporting the customer in his approach of even more complex architectural design and give the appropriate solutions for it and the most cost-effective solutions for it. So I think, this is what we can do in the real world. And I will now join and hand over back to Gerard to explain you the benefits we jointly can offer Arista and SDNsquare.
Thank you, Henry. Well, I think it's you first, actually. So very quickly, just to kind of recap of the benefits of the joint solution. It works and it's future-proof. So
yeah, Grid, we will set absolute guaranteed flows, whether it's a random IP network with very specific and predictable bandwidth. So whether the flows are containing live IP, file-based, file transfer, audio, it doesn't really matter. We will make it work, and with the use of links up to 100%. So we will not over provision the network. We will really use 100% of the link offered by the network and by the switches.
So in terms of future-proofing, then we're building this on merchant silicon, delivering anywhere from a gig to 400 gigs today and 800 gigs tomorrow. And of course, it's all sat on top of a software platform in EOS architecture from the ground up to deliver all of the stuff that broadcasters need: reliability, extensibility, programmability. Tell us how it simplifies and automates and reduces risks.
So yes, absolutely. So IP network configurations, flow managements will be reduced with a very, what you see is what you get tools, so our user interface with automatic generation of command lines, very important to accelerate and ease the deployment of network, and also to guarantee error-free deployment of the network.
I think a lot of what Henry's talked about so far today, it just tells us how important flexible and fast APIs are to allow external devices, external control surfaces to directly manipulate traffic in a way that normal networks wouldn't do, but in a way that our specific broadcast networks absolutely need. And I mean, whilst there's a lot of tools available in the Grid system, you still need a network guy to do quite a lot of stuff. So having this single EOS binary really simplifies the kind of life cycle of the NetOps guys, reducing cost and improving uptime, which is vital to the broadcast guys.
Talking about the business and the financial solutions we can offer by reducing the total cost of ownership, using more traffic and less staff. So the tight management of all the flows and building large installation with top-of-rack switches will allow us to reduce the cost as much as we can, and to deliver also 2 to 4 times more traffic that it used to be with other type of software-defined network controller. So engineering costs, service costs, maintenance costs will be also reduced by using more automation and more control and monitoring software.
And that's absolutely in line with what we see with pretty much every other group of customers using rich data, streaming telemetry, the technologies we've got to push information about the state of the network up to higher level tools to make more application layer decisions, basically driving down human errors and speeding up deployments using automation. It's absolutely all in there. With that, I think, Seb, we're back to you.
All right, thank you very much, Henry. Thank you very much, Gerard. On the behalf of SDNsquare and Arista, I would like to thank you all for taking time to join us today. If you have any follow-up questions, please do not hesitate to reach out to either SDNsquare or Arista. And if you wish to rewatch this webinar, the recording will be available in the next few days, and you should receive an email in your inbox. With that, thank you very much, and have a good day. Bye.